In this tutorial video, I will introduce PCED, a computer software for poly-crystalline electron diffraction simulation and phase identification. This is one of the main components in Landyne software suite for electron diffraction simulation and crystallographic analysis. You may download the software suite, including user manuals, from the website on the screen. Double-click this to start the launcher. If you purchased a license, please copy the license file to Landyne 3 folder and Programs subfolder. Let me show you. In my case, this PC, and go to C folder, Landyne 3 Programs, and here are the PCED 3, and this is PCED 3 license key. Click this icon in the launcher to start the PCED program. A license dialog will pop out in case you don't have a license file. Then you may select the demo mode to continue. In the menu, first is crystal. The first one is for you to prepare a new crystal file, and then you can load phase 1, load phase 2. Only 2 phases allow to simulate it at the same time. Exit will leave the program. In experiment, you can load experiment diffraction pattern, show which file name is. You can erase the pattern. A few processing allow you to invert the brightness, and you can adjust the grayscale, and you can resize and rotate the pattern. You can make alignment the pattern to the center. And then this one is for you to do the calibration to adjust the G spacing marker. And for the phase identification, you are allowed to show the diffraction pattern in the half of the screen. Other half will be the simulations. In simulation, we have the theory, kinematic diffraction theory, and dynamic diffraction theory to select it. And you're allowed to define the crystal average grain size, the peak profile, texture model, and you can index diffraction ring, and there are a tool for you to change between Miller-Brave indices and the Miller indices. And this parameter table is this table here. And you can show all of them or hide all of them. In pattern, we have a region of interest for you to save the area that your interest, and also the TIFF for TIFF file resolution. The file can be saved in JPEG or TIFF. You also can save diffraction and intensity list, including other options which can be defined in the preference. In table, we provide a element periodic table like this, and also the space group table like this. You can search for the symbol of each space group with a number and symbols. These tables allow you easily to prepare the new crystal face. In help, you have a current drive and SN serial number. Click here and you got this number here. You can take a snapshot of this dialog window and send to us for us to prepare the license file for you. The last one is version. The drop-down menu includes all the functions. Graphic menu bar is only selected part of them, which is important, can be used conveniently. The only one exception is the drag and drop box, only available in the menu bar. Now I will show you how to create a new structure file. If you already watched the other Landyne tutorial videos, for example SAT3, and are familiar with how to prepare a new structure file, you may move forward to next topic. Landyne software suite is distributed with a collection of structure files, so you can use PCED3 immediately. I'll show you where the structure files are. In this PC, C folder Landyne 3, and see here structures, and all these structures already made. Let's do the PCED pattern simulation now. We can load the new crystal file from load phase 1 or load phase 2. We also have a default file already here, aluminum default. In the second phase, if we select here, magnesium default, we can show this table. We can enlarge this table. This is parameter tables. When you load a new structure files, those files will be seen in this table. Aluminum default and magnesium default. The simulation allows you to simulate in phase 1 or phase 2 or phase 1 and phase 2 together. All the parameters about the simulation is shown here. File name, the key factor will control the profiles, and the grain size. This is in plane, and this is the height, and the texture defined as out of plane along to 001, and the match factor also control the textures is selected as a 1. We just introduced the structure file and the parameter for simulation. The other parameter are given here in calculation. The high tension is 200 kV. You can change any high tensions that in your max scope. And this G max is set as a 1.0, 1 over angstroms, and this gives you the largest G value in the simulation. Currently we use kinematic diffraction theory. And here are the mass. If you use two phase here, start point is 50-50. If I use only one phase here, there will be 100. If using the second one, and the other part is 100. Let's try the first with the aluminum. And here we have the G spacing zoom. Start point is 1.0, and here are the intensity scale 1.0. Simulation is simple. Click calculate. Now we have the aluminum diffraction peaks. This is like in the X-ray powder diffraction case. We can zoom this one. We can increase the, and if I calculate the magnesium, I'll disconnect this one. We can show both phases together, one in red color, one in the blue color. As you remember, in the patterns options, we can reset the peak colors for phase 1 and phase 2 here. Default is blue and red. In two-phase case, we can adjust the mass ratio of this two phase. And you can see magnesium phase diffraction is reduced. If you move to the other side, aluminum phase mass is and also peak reduced. This one, when we do simulation, we can roughly estimate it. If you have a two-phase case in your sample, the mass ratio is just roughly estimate for this two phase. Now we leave one phase there, remove this one. We change the Gmax to 1.5 and do the calculation again. And you can see that more diffraction peak come out. We'll go back to 1.0, do it again. You see that cutoff for the high G value peaks. And now we're going to show you the profiles in the simulation. And here is show the peak and profile together. If we show the profile, no peaks, it's showing in the shadow like this. And the profile is, of course, controlled by grain size. We'll show that later. You can select solid or just the curve. So this is the curve, and this is solid, and this is peak only, no profile, so just peak position. Normally we have all of them on with the solid shape. And for teaching, and we also can include the background causing by the incident beam. So the incident beam included now, and this give you some background to the peaks. And you can control, depending on the exposure time and the beam intensities, you can control the beam. This is a long exposure time or a very strong. And you can change the pseudo widget, the functions. I will show you different profiles. In addition to the simulation in kinematic diffraction theory, simulation in dynamic diffraction theory is also adopted in this program. You can select the simulation theory, and here dynamic. Then you have a dynamic diffraction theory. The calculation in kinematic diffraction theory is much faster and accurate enough for phase identification. The simulation in the dynamic theory can use for teaching or some special case in the research work. The background on the theory can be found out in the reference in the user manual. Now we use the default file aluminum to compare these two simulations. First, we get the grain size dialog from here. And here are constant K, we can control the profiles, mostly related the full width at half height. And the diameter is in plane, and let's change it to 100 nanometers. And the thickness is for 100 nanometers. And this is for phase 1. And do the calculation. This is for the dynamic diffraction. Now let's look at this phase peak height and select it here, kinematic diffraction theory, and do calculation and pay attention to this height. Reduced. The other height also changes slightly. And for the simple aluminum phase, it shows slightly different result for the dynamic theory and kinematic theory. Now I explain to how to index the diffraction peaks. Here are the indexed labels. Move this down. And see here are phase 1, and we have phase 1 here. Once we selected the phase 1 index, immediately here show the index for aluminum is 1. Adjust this top line and baseline, we can position of our index label to ideal position. So let's see, top point, click in the display area, and I lower the top point, and now the labels are more separate, and I go high, this label were more close to each other, and I can move the top point on the left and right will control all the labels come to right or left. If I have a two-phase here, and I put the second phase on and do a calculation, so now it's a little complicated. Of course, you don't want to show the guideline to people. So for the second phase and the first phase, and I will select not show the guideline. But still, this, now we got the whole pattern are indexed for two phase. The aluminum phase is in the first line, magnesium phase in the second lines. Now I explain how the texture or the preferred orientation affected the diffraction pattern. Let's change it to the G max to 1.2 and calculate. This is in simulation texture model. The texture model we use is March texture model, and watch how the intensity changes if I change this March parameter here after calculation. See this 200 peaks going up and more because of this near full texture 001. So the 200 peak and 001 are the same for the cubic. And when we have a full textured, then we only have the 200 very high, and so totally change the pattern of diffraction. And let's go back and watch the 111 peak going up, and this is total random. 111 peak is the highest peak. Let's look at it for 111 orientation for texture. Calculate. And see, this peak disappeared. And further, 220 going up and further. And finally, for the 111 orientation in extremely case, 11220 are only peak appeared. There are two ways to load the experimental diffraction pattern. First one is traditional using Windows file system. The second way is first find out where the diffraction pattern is. Then you can drag and drop to the drop box to load it. Hold your mouse left button and drag it. And you see here a move sign show up and release it. You also loaded your diffraction patterns. You can make several image processing before do the phase identification. Image processing in the experiment menu. Move your diffraction pattern to the center, the shift and the center EDP. You click here and multiple ring will come out. You can control how many rings appear here. Let me put 5. So there are 5 of them. So your selection of how many. The circles there, and you can show or not show. With reference to the green ring, you hold your mouse left button. You can make a small adjustment. So make the ring perfectly match with the reference ring. To calibrate the G spacing zoom factor. This first ring is 0.4277 1/4 angstrom. Let's go to experiment menu bar, adjust the G value, so is 0.4277 1/4 angstrom. But this marker is not on this ring, so we need to adjust the G zoom. You can click here and use the arrow key. And now you see the position and also the intensity scale. The first ring is most intensity one, and second one are here, and so it's a perfect match. So this one is identified as aluminum. We have another way to show the experimental pattern to half. So in this case, you can put the ring tab half or full. If we put a full ring here, you can see the ring position and the intensity scale there. And you also can put the half ring here. And this quarter area, we can put the index label here. So making the whole pattern experiment, simulation, and index. To show the index. So we have all the diffraction peak indexed. You can save the display area to a file, either JPEG file or TIFF file. Before you save, please check ROI and TIFF. This is show where you want to print out. This is the maximum. If you reduce this a little bit, you can see the blue square. Inside the blue square will be saved to the image. Thank you for watching. Please check our other videos about Landyne software suite for electron diffraction simulation and crystallographic analysis.